And because of this, sometimes for open methods, it may happen diversion. So it may diverge from the true root. So diverge, apa maksud converge and apa maksud diverge? Okay. Okay, converge, it means every time we do iteration, so converging increment, each time we increase the iteration. So from the first iteration we go to the second iteration, what will happen? The value of x will converge towards the root. Katakan ini kita punya root. So nilai x kita akan sentiasa menghampiri nilai root. That's what we call as converging. While diverging means our x value will stay away or will run from the root. So this is our root. So our x value will keep going far away from the real roots. That's the meaning of diverging and converging. So the diverging and converging happens. How converging and diverging happen? It will depend on the initial value that you choose. One of the reasons diverging or converging happen is depends on the value of x I that you choose as your initial value. Sometimes when you choose an xi value, it will your solution will go diverge, so away from the roots. And if you choose the correct initial, then you will get an iteration where your solution is going to converge towards the root. So picking the initial value is very crucial when you choose to use open methods. So pemilihan nilai initial tu penting bila kamu nak buat open method, supaya kita nak dia converge. Kita tak nak dia diverge. Okay, kenapa ini boleh berlaku? Okay, kita kena ingat when we do open methods, okay, bila kita tengok each of methods that available, so we will start off with fixed point iteration. We actually, bila kita ambil satu titik xi ni, kita akan cari dia punya berapa kecurunan kat sini. And then kita cari dekat mana dia akan cross dekat axis x. Then kita akan dapatlah next point of kita punya iteration. So kalau kita tengok kat sini graf ni, dekat sini dia makin landai kan. So kalau you ambil dekat dengan 0, x dekat dengan 0, so tangent line dia akan dapat lagi jauh. And then kalau jauh dia tu sampailah dia pergi kepada the next slope yang makin turun ni, so dia akan tunjuklah semakin jauh lah pergi. Tapi kalau kamu ambil titik yang hampir dengan root ni, for example in C, so bila kita buat tangent line dia, kita akan dapat dekat sini, and then the new xi, kita dapatkan fxi yang baru. So kita buat lagi tangent line, dia akan makin hampir dengan root. So ini yang kita nak lah. So pemilihan x, nilai x itu adalah penting untuk open method. So let us look at simple fixed point iteration. In fixed point iteration, the first thing that you need to do, if you are given an equation, is you need to rearrange the function. So when we rearrange the function, we want our new equation to be like this one. So kita nak dia jadi dalam bentuk gx is equal to x. So that x is on the left side of the equation or the right side of the equation, and we have g of x on another side of equation. And when we use fixed point method, sometimes it may diverge, but this is depending on the starting point that you choose or initial guess that you choose and how the function behaves. So either it will diverge or not will depend on the function of g of x and what is the initial value that you choose. Okay, the first step, how to rewrite the equation. Let's look at example on how to do this, how to rewrite any equation into the formation that needed by fixed point iteration. So the only thing that you need to remember is this one. This is the form that we want to rewrite to. Let's say you are given, this is your equation. This is your fx, or x squared minus 2x plus c equal to 0. So when we want to rewrite in terms of fixed point iteration forms, so what we'll do, we want to, in this case, so we find what is x. So x is equal to, so we move x squared and 3 to the other side of the equation. So we get x squared plus 3, and then we move this 2 to the right side. So we will get equation like this. So this equation has now been written in this form of equation, where on the left side we have x and on the right side we have gx. So our gx in this case is equal to x squared plus 3 over. So this is the first step on solving using fixed point iteration. How about, let's say we have sine x equal to 0. So our fx equal to sine x equals 0. So how can we write this in this form? So sine x equal to 0. So we can rewrite this because there is no, the only x here is inside this sinusoidal function, right? So in order to rewrite as x and g of x, so what we can do is we can rewrite this as sine x is equal to x minus x, because x minus x is equal to 0. So now we can rearrange this equation into, so we move this to the other side. So that's how we can get x is equal to sine x plus x. Okay, are we clear?
Yes, sir.
So how about this? Let's say we have exponent negative x minus x is equal to 0. So can we rewrite this in this form? So we will get x is equal to exponent negative x. If our function is only a single term with x, then we need to assume that, okay, we have on the other side we have x minus x, then we can create in this form. But if our function involves multiple terms, then it will be easier, straightforward for us to find or rewrite the function into a fixed point iteration equation. Okay, let us look at more examples. Okay, this time we have a polynomial fx equal to x squared minus x minus 2, where x is greater than 0. So for this case, we have a multiple option on how to create our function of g of x. Okay. First, we can say that, okay, let us take this x. So our gx, so if we take this x, so we move to the left side, so x will be equal to x squared minus 2. So this is our x, this is our gx. We can also say that, so instead of moving this x, so we want to move this x squared. So if in that case, so we'll get our gx equal to square root of x plus 2. Also, we can also have gx in this kind of form where gx is equal to 1 plus 2 over x. So we have, in this case, we have 3 versions of gx that we can use to solve fixed point iteration. Okay. Or let's say we have this f of x equal to x squared minus 2x plus 3. So we can have our x is our gx equal to x squared plus 3 divided by 2. Or we have f of x equal to sine x, so same as the previous example. So x equal to gx, so x equal to sine x plus x. And the last one, fx equal to exponent of x over minus x. So x is equal to exponent of negative x. So this is an example of various on how you rewrite each of the given function in terms of x equal to gx. So next, what we need to do in order to solve this using simple fixed point iterations. So the next thing is, after we express the function in terms of x and gx, what we can actually do is we can treat each of these as a pair of equation. Let's say x as y1 and gx as y2. So when we plot these two functions, x and gx, so let's say we plot x and we plot gx. So when these two lines cross each other, so that's the point of our root. So when we rewrite the function in terms of x and gx, and if we plot those two functions, what we're actually trying to do is we want to find the intersection of those two lines. And the intersection will give us the valuable information, which is the root value. So that's what we are trying to do when we solve this by using numerical method. So we break it up into two functions. We find the intersection. So we want to find the intersection value. So the intersection value will give us information about the root. Okay, so for fixed point iteration, this is the main formula for a fixed point iteration, where the next point of x is equal to function of g of xi. So we will, for simple fixed point, we will use this equation. So we need to find what is g of x, and by using the old value of x, we can find the next value of xi. But one more thing that you need to know, that in order for the fixed point iteration to converge, you need to check the first derivative of gx must be always less than 1. So if this condition is fulfilled, then we know that our fixed point iteration is going to converge. Instead of lawan boleh converge adalah diverge. So kita nak dia diverge, kita nak dia converge. So kita kena check. Kalau G prime X is less than 1, so kita tahu dia akan jadi converge. Okay. So we know that. So one more point. First kita tahu the convergence or divergence bergantung kepada, first is the initial point. Initial point satu, either it is converge or diverge. First, it will depend on initial points. Now we know that the divergence or convergence will happen based on the chosen function of gx. Okay, in this figure, for figure A and figure B, both method for both example will converge. So when we do fixed point iteration, both will give us convergence, where our next value of x will always going towards the root value. While for C and D, by using this function of gx, even though our value of x naught is very near to the roots, but if we choose a wrong function of gx, it may diverge from the root. Kalau kita compare, you can pakai A dengan C, you comparekan B dengan D. Okay, A, initial point kita jauh daripada root kan, tapi oleh kerana kita pilih a correct function of gx, so ataupun kita punya G prime X is less than 1, the magnitude of G prime is less than 1, so dia akan converge kepada root. In C, our G prime X is greater than 1, so kita punya, even though kita boleh X naught ni dekat dengan root, tapi dia akan pergi jauh daripada root. Sama juga dengan D. Even though X naught kita ni dekat dengan root, tapi oleh kerana kita pilih GX, kita tu salah, so dia akan diverge, pergi lagi jauh daripada root. Kita dapatlah nilai root. So kita know, now we know that in order for to successfully solve by using fixed point iteration, we need to make sure that our initial point, we choose a correct initial point, and our G prime X is less than 1. Let us look at one example related to a simple fixed point iteration. Let's say we have a function exponent negative x minus x. So the first thing, we need to rewrite in this form. So we will get g of x equal to exponent negative x. So by using the fixed point iteration formula, so x sub I plus 1 is equal to g x sub I plus 1 is equal to gxi. So we can rewrite this, we can write it as this equation. So we start our initial guess by x not equal to 0, and then we can find, so we're starting off with I equal to okay, x not equal to 0, then we can find what is the value of x1, x2, x3, and so on. So x1, in order to find x1, so x1, so I equal to 0, x1 is equal to exponent negative x0. So x0 is equal to 0. So for x1, we actually, our x1 value is equal to exponent negative 0, which is 1. So we continue the iteration. We will continue this iteration. So next, we will replace the value of x. So for x2, so when x2 I equal to 1, so it is So our x2 is equal to exponent negative x. Sorry, oops. So x2 is equal to exponent negative x1. So our x1 is equal to 1. So when we try to calculate x2, so x2 equal to negative 1. So it seems that every time we do iteration, our next value will base on the previous value of x. So if we do this, we can summarize it in this table. So this table summarizes what the iteration that we need to do for a simple fixed point iteration. So when I equal to 0, so xi equal to 0, our initial point, so g of xi equal to 1. So this will give us the next value of xi, which is 1. So each time we do iteration, the outcome of gx will be the value of x that we will use for the next iteration. And if we calculate the approximate error, the relative percent approximate error, okay, it seems that, or it's shown us that the value of epsilon a is getting smaller. Okay, let us say that 1.11% is enough, or it is confident enough for us to say that the value of xi is actually our root value. Then we can stop. So by until 10 iteration, so we keep doing this iteration until 10 iteration, so we'll get our xi is equal to 0.564879. So we can say this is our estimated root for this equation. All right. So this is, let's say this is our final answer lah. So by using fixed point iteration, okay, after 10 iteration, we can say that, okay, our xr is equal to 0.464879. If you can calculate the real root for this equation, then we can find what is the true error of your answer. All right. Okay. Do you have any question? It is very simple. Okay, just use the given equation, rewrite it into this form, and then use the equation to complete this table. So usually for fixed point iteration, we will find what is the value of xi, what is the value of gxi, what is the epsilon a value. And usually the question will give us either what is the stopping criterion, the pre-specified error that you need to use, or the maximum iteration number that you need to utilize. Okay. Okay, let's do one more question as exercise. Let's say we have this equation. So use simple fixed point iteration to locate the root by using the initial guess 0.5. So the first step is to rewrite this equation in terms of x and gx. Okay, so straight away, okay, this is, okay, we can say that x is equal to 2 sine square root of x. Easy, very easy, right? So we have done the first step. Next, the next step is what? So rewrite in terms of the function of fixed point iteration. So x sub I plus 1 is equal to g of xi. So we know this is our gx. So x sub I plus 1 is equal to 2 sine square root of x I. Okay. So what we can do is, so we build up the table. So we will get this kind of table. Okay. So if we complete, okay, let us see, okay, the first iteration, of course, in order to get this table, you need to calculate each iteration lah. So you still need to do the manual calculation for each iteration. So the first iteration, so for x1, so you get 2 sine, so we square root of 0.5, you get 1.299274 for gxi. Okay. And then how to calculate the epsilon A. So epsilon A, remember so we will look at the value of xi. So the new value of x minus the previous value of x divided by the new value of x. So 1.299274 minus 0.5 divided by 1.299274 times 100%. So we get 61.517%. So we'll keep doing this iteration until, let's say in this example, so we continue with the remaining iteration. So in the previous slide, so we have done until this step. So we continue this, okay, by using the same equation, which is 2 sine square root of x. So we will keep changing the value of x based on the previous calculation. So if we look at the epsilon A value until we reach 7 iteration, I equal to 7, or the 8th iteration, we can actually see that the value of epsilon A has dropped very low until 0.02%. If you are satisfied with this approximate error value, then we can stop and we can say this is our approximate root value, which is 1.972377. And we can check this. You can replace this x value into this original equation and see either it is equal or to 0 or not. You can always do that. Or if you can find the true root, then you can find the epsilon t value, or you can find the true representative error, or you can find the true error value. And if you want to program the fixed point by using MATLAB, so you can follow this given flowchart. Where for this flowchart, the input will take 3 conditions, which is the initial value, the value of epsilon s, the pre-specified error, and the maximum iteration value. Where for this flowchart, what will happen? The iteration will continue to happen until the approximate, the value of epsilon A is greater than, if the value of epsilon A is less than the value of epsilon s, or the maximum iteration have been reached. So katakanlah you buat iteration tak dapat nilai epsilon A tu, tak dapat rendah daripada epsilon s, tapi kita dah bagi, katakan maximum iteration adalah 10. So bila dia reach 10 walaupun tak dipenuhi, maka dia akan berhentikan computation tu. So dia akan stop lah program. So dia tak akan loops forever, dia akan loop forever loop lah. Dia tak akan terperangkap dalam loop tersebut. Okay. Ada soalan berkaitan dengan So habis untuk fixed point iteration. So do you have any question related to fixed point iteration? Fixed point iteration yang penting tu yang ni lah. X I plus 1 is equal to G X I. So ini formula yang penting untuk fixed point iteration. But the next point will always be given by the function, the value given by the value of x to the function of g. Okay, kalau tak salah kita move on to the Newton Raphson method. Okay, Newton Raphson method is the most widely used method in open method category. So kita ada open method category, Newton Raphson ni adalah yang paling banyak digunakan. Where this method came from? So it came from the Taylor series expansion. So kita dah tengok about Taylor, we have discussed about the Taylor series expansion when we learn about the mathematical modeling. So if we have a Taylor series expansion and we tend to find what is the root of this Taylor series expansion. So the root of the root is in for Taylor series expansion when our fx sub I plus 1 is equal to 0. So whatever value of x sub I plus 1 yang mengakibatkan fx equal to 0, itu adalah root dia. So by rearranging the series, okay, let's say we have this is equal to 0, then we can develop a Newton Raphson formula. So kita tengok sampai kita tengok untuk sampai first term saja. Kita ambil sampai sini saja. Kita ambil sampai sini saja. Okay. So if fx I equal to 0, then we will get this term. And if we try to solve this, so kita nak yang ni. Kita punya target adalah kita nak tengok what is the value of the next value of x. Itu yang kita nak. So if we try to solve this, so we rearrange this, so we'll get a Newton Raphson formula. So oleh itu terbentuklah Newton Raphson formula yang mana x sub I plus 1 is actually xi minus f of xi divided by the first derivative of f xi. So f prime xi. So untuk Newton Raphson formula, you kena buat kerja lebih sikit. Yang mana kita perlu cari apa itu f prime x. And then barulah kita boleh selesaikan this Newton Raphson formula. Okay. In term of graphical, so macam mana Newton Raphson ni bekerja adalah, okay, apa yang Newton Raphson ni buat, okay, bila kita pilih satu titik x. So, saya clearkan ini kejap ni. Okay, so bila kita pilih satu initial point x, okay, apa kita buat? Kita akan cari apa nilai fxi dia. Okay. Bila dah dapat fxi dia, kita cari f prime xi, slope dia. Tujuan kita cari slope adalah kita nak buat satu tangent line. So bila kita ada satu tangent line, we will extend this tangent line. Kita nak cari dekat mana tangent line yang akan cross x-axis. So the point where the x sub I plus 1, the new point cross x, itu adalah nilai xi plus 1 kita yang baru. So daripada sini, so kita tahu tinggi ni adalah fxi, jarak di antara dua ni adalah xi minus xi plus 1. So f prime xi adalah this one. So from this one, kita boleh dapatkan apa nilai xi ni. So kita rearrange dia. So kita akan dapatlah ini, iaitu formula bagi Newton Raphson. So untuk Newton Raphson, apa kita buat? Kita perlu cari first derivative. So let's see the same example that we have used before. So fx equal to exponent x minus x. So employ initial guess of x not equal to 0. Okay. So the first thing is we need to find the first derivative. Ini kita tak perlu. Kalau simple fixed point iteration ni, kita kena rearrange dia jadi dalam bentuk x dengan gx kan. So ni tak perlu. So daripada function fx yang kita ada, you just cari first derivative f prime x. Apa dia f prime x? So dah dapat f prime x. Okay, then kita masukkan dalam formula Newton Raphson yang ada, iaitu this formula. So kita akan dapat, so we can create from the original function, we can create a equivalent function of Newton Raphson for each function of each given function. So kita dapat xi plus 1 is equal to xi minus f of xi, which is this one, exponential xi over minus xi, divided by the f prime x, which is this one. So now we have the formula. The next thing is to compute. So for each iteration, so for each value of I, what is the value of xi? And what is the value of epsilon A? So that's the only thing that we need to do. So okay, we can create a table. So of course, in order to get this table, you need to manually calculate. So for we start out with I equal to 0. So xi, our initial guess is xi equal to 0. Then xi plus 1 is 0.5. So how we get this one? So when for xi plus 1, so for x1, so we got x0 minus f of x0 divided by f prime of x0. So 0. So we get our value as 0.5. So when our I equal to 1, so our xi is 0.5. So we take the previous value, the old value, as our the current value of when I equal to 0 will be used as the old value when I equal to 1, and then we can calculate this one by using this formula. So by substitute xi as 0.5, so 0.5, 0.5, 0.5, and 0.5. By using calculator, calculate it. So we get xi plus 1 is 0.5663103. Then we calculate what is the approximate percent relative error. So by using this value, so we can calculate what is the approximate error. So we get 11.8%, and if we continue with this iteration, when we reach I equal to 4, or the fourth iteration, we will get our approximate error is less than 10 power of minus 8, and the value of xi, and our value of xi, we can use it as our root value. So if we compare by using Newton Raphson and with the previous fixed point iteration method, we can see that by using Newton Raphson method, the approach will rapidly converge on the true root. So we only need 4 iterations to get such number of epsilon A. Kalau kita tengok yang sebelum tadi kita buat sampai 10 iteration pun kita masih dapat epsilon A yang tak sekecil ini. So, but by using Newton Raphson method, kita akan dapati bahawa dia akan improvekan kita punya convergence dan dia lebih cepat converge berbanding dengan fixed point. So that's mean that by using Newton Raphson method, we can solve it faster compared to the simple fixed point iteration method. Okay, ada soalan? So dekat slide ni ada kesilapan di sini epsilon A. This is epsilon T. 2% relative error.
Sir,
Yes.
kalau dalam exam kan, macam formula-formula tu dia bagi ke?
Formula yang mana?
Macam formula untuk cari
Yang ni?
XI tu.
Yang ni? Formula yang ni? Selalunya dia berilah. Tapi tak adalah susah sangat. Tak adalah kompleks mana nak hafal pun kan. Tapi selalunya diberilah. So Newton Raphson apa XI. This is general formula dia. Fixed point apa dia punya general formula dia. So dia akan diberilah. Cuma tak tahu nak pakai je lah. Alright. Okay, so sama juga if you want to program this Newton Raphson method in MATLAB, so you can use this flowchart as a guide to program using MATLAB. Although the Newton Raphson method is often very efficient, but there are situations where it will perform poorly. There are some special cases where we try to solve multiple routes. We'll find how this Newton Raphson cannot be used or inefficiently used to solve multiple routes. So we will see this case later on. Somehow or other, there are sometimes even when we're dealing with a simple routes, difficulties can also arise. So we can see in the following example. So in this 4 example, it shows us 4 different cases where the pitfall of Newton Raphson method happens. So in example A, what we can see here for this function, when we try to solve using Newton Raphson, it looks like we start off with x0. Okay, we find a tangent line, then we get a new point x1, we get a new tangent line. So it seems that we are not converging. So we are diverging from the root. Same also for B. So B, so we start off with a point far away from the roots. So what will happen here, so every time we do the iteration, it seems that it will focus on this region. instead of going towards the root. Ini masalah function ni lah. Masalah function fx. Dan juga masalah bila kita pilih nilai initial point yang tak bersesuaian lah. Okay, in C where we have multiple roots, so sometimes what will happen, so we are missing the converging to the roots. And same goes to the D. So for D, there is no roots available here. So we will forever be looping in iterations where we will never get the answer. This is some of 4 cases where the Newton Raphson cannot be used to solve the given function. Ini bentuk yang berlaku dia sama ada dia diverge ataupun dia bertumbuh dekat satu region sahaja, ataupun bila kamu buat tu memang tak ada root, memang solution tak ada root. So guna Newton Raphson tak akan dapatlah root dia. This is the sample example of cases where you will not get the root when you use Newton Raphson. In certain cases, sometimes the convergence can happen, but very, very slowly. So, kita tengok contoh. Let's say we have this function, fx equal to x power of 10 minus 1. So, kita cari f prime x equal to 10 x power of 9. Okay, so we build based on the general Newton Raphson formula. So, we will create a new equation as follows. So, if we compute using Newton Raphson, this is what we get. Okay, starting with initial guess of x is equal to 0.5. So if we try compute, we will get this kind of result. So we start out with x equal to 0.5. So x, the next x, so x2, if we calculate this using this formula, we get 51.65. So it jumps from 0.5 to 51.65. And then what will happen is it will slowly converge. So from 51, it will slowly drop to 46, 41, 37, 33, and 30. If you plot this graph, you can see that you can find what is the real root of this equation. So when we use Newton Raphson here for this case, when we reach the 14th iteration, we only get our xi is equal to 14.587. In order to reach x equal to 1, you need lots of iteration. That's why it labeled here as infinity. So if you reach infinity, then the only time that your x you will get only equal to 1. So the converging happens, but very slow, at a very slow rate. So in terms of computational time, it is not worth. You can find the roots, but it is not worth. So what option that you have? So the only option that we have, we can use different method to solve this equation. Okay, let's another example. Let's say we have a polynomial equation. So let's say our fx equal to -1 plus 5.5x minus 4x squared plus 0.5x cubic. So we determine the real roots A graphically and B by using the Newton Raphson method to a pre-specified within the pre-specified error, which is equal to 0.01%. So there is no initial value given this question. So you are not given initial value. So what value that we need to choose in order to start with our Newton Raphson method? So that's why this question asks you to graphically find the roots. So if you draw a graph, so by using a graph paper, or you use any software, you use a MATLAB or you use an Excel to plot the graph, okay, we can estimate the initial value that we can use. So if you plot the graph, you can see that there is 3 roots available in this function of fx. The first one is nearly 0.2, second is nearly 1.5, and another one is at 6.3. Itu kita punya berkata kepada apa tempat lah kita plot graph tu. So kita kata di 0.2, 1.5 and 6.3. So kita punya real root kat situ. Okay. So when we want to try solve using Newton Raphson, so we need to choose our initial value. So for the first root, so kita tahu root tu berada dekat dengan 0.2 lah. But we didn't know what is the exact root value. So to make it easier, we choose any point that is nearer to this root. So for the first root, we choose x, our initial x as 0. Of course, before that, we need to find the first derivative of fx. First derivative of fx, we need to calculate. Okay. And then we do the iterations. So if we solve for the first root, so by using the initial point as 0, by the fourth iteration, we will get our xi is equal to 0.214333, and our epsilon a is 0.00408, which is less than the given epsilon s value, where our epsilon s is 0.01%. So when we reach fourth iteration, so we get our epsilon a less than epsilon s. So we can stop and you can see that this is our answer. So our first root will be at 0.214333. For the second root, so we know that this second root is nearby this value of x. So you can choose, let's say you want to use x equal to 1. So go on, there is no harm. So in this case, in that example, so we choose x equal to 2. So we choose x equal to 2. So by using x equal to 2, we do the iteration by using the same Newton Raphson formula that we have modified. Okay. So until when and our indicator is by looking at the value of epsilon a. So once the epsilon a is less than the epsilon s, so we know this is the time that we need to stop by the fourth iteration. So our epsilon a is less than epsilon s, and this is our root value, which is 1.479769. And for the last root, so we choose our initial value as 6, and we try to solve it. So by the fourth iteration, we see that our epsilon a is less than epsilon s, and this is our root value. So we can say that by using Newton Raphson, the roots are available at 0.214333, 1.479769, and 6.305898. So this is our answer. So in order to get all this table, of course, you need to manually calculate. So the first iteration, what is the value of xi? what is the value of fx, what is the value of m prime x, what is the value of epsilon a, and then you can fill in this table. Kalau you buat secara manual lah. Tapi kalau you gunakan you solve it using computer, and then you, of course you boleh dapat terus this table lah. Right? Ada soalan kaitan dengan Newton Raphson? Okay, even though the Newton Raphson looks very promising compared to the fixed point iteration, however, there are some drawbacks for Newton Raphson. Newton Raphson method require the calculation of the derivative of a function. So you need to find f prime x. And sometimes, if you have a very complex fx, then finding the derivative is not always easy. And if f prime vanishes at an iteration point, so when you do iteration, sometimes when f prime vanishes, then the method will fail to converge. Then if it fail to converge, then you cannot solve the Newton Raphson. Or when the step is too large, and where if it is too large, it pointing to another route. So macam ni. Apa dia maksud? If the step is too far, untuk contoh this one. Right, for this one. Bila dia punya step too far, supaya kita nak cari route yang ni kan. Kita pilih X ni, kita nak pilih route yang ni, tapi dia dah too far. Dia dah lari daripada route asal yang kita pilih, kita nak selesaikan. Itu maksud dia bila step tu terlalu besar. So when adapun kadang-kadang value is oscillating. So oscillating dekat satu tempat je. So in that case, ada more conservative method. So kita boleh pertimbangkan method lain yang kita boleh gunakan untuk selesaikan. So kita tak boleh selesaikan gunakan Newton Raphson. Okay, ada persoalan?
Tak ada, Sir.
Okay, kalau ada soalan, kita break kejap 5 minit. Hari ni seperti yang dijanjikan, so hari ni kita ada quiz. So quiz akan bermula pada pukul 12.30 sehingga ke pukul 1. Yang mana saya dah schedulekan dia dekat dalam assignment tu. Nanti 12.30 dia akan pop, notis akan keluar. Dia boleh mula menjawab lah 12.30 nanti.
Okay, Sir.
Right. Okay, let's continue with second method. So we know that one of the problem with Newton Raphson is we need to find derivative. So we need to find f prime x. There are some cases where for a certain function, the derivative may be extremely difficult or inconvenient to evaluate. So for polynomials, it doesn't give us any so much problems. But if our function is very difficult to find the derivative, then we have another method that we can use. We can use second method. So for second method, what it actually do, it will base on the Newton Raphson method. Okay, if we can't find the derivative, or derivative cannot be computed analytically, then we need to compute it numerically by using a backward finite divide difference method, so that we can change our Newton Raphson into second method. So let us see how this is possible. So if you remember, okay, this is the formula for Newton Raphson. So let us focus on this derivative. Where this derivative came from? So this derivative is actually from here. So f prime x is actually df over dx, correct? And how to find df dx? So df dx is the change of f. So f of xi minus f of xi minus 1. So we are using a backward finite divided difference method. So df is actually a change of fxi and fxi minus 1, and dx is the change of xi and xi minus 1. So next we take this term and we'll substitute into this equation. So if we substitute this into this, then we will have what we call as second method, where x sub I plus 1 is equal to xi minus fx times, so this one you will replace this one, so we will get xi minus x sub I minus 1 divided by f of xi minus f of x sub I minus 1, where I is equal to 1, 2, 3, and so on. So now we can have a new method we call as second method that not depend on the derivative function. So you don't need to find f prime x to solve by using second method. But you need, instead of for the previous method, you need to have one initial point. But for this second method, you need to have at least two initial points. So that's the only difference. Instead of using one, you need to have two initial points. But these two initial points doesn't have to be a bracket. So you can choose any point. In this example, we choose xi and x sub I minus 1, where these 2 points is not situated or the roots is didn't exist between these 2 points. You can have point that not bracketing the root. So tengok, dua point yang kita pilih ni tidak menjadi bracket kepada root ni. Kalau bracket dia mestilah satu titik berada dekat sini, satu titik berada dekat sebelah sana lagi kan, supaya dia bracket. So untuk open method, dua-dua titik tu berada di mana-mana yang tidak bracket kan root. So even it require 2 initial estimate, but it is not a bracketing method because the chosen point is not bracketing the root. Itu yang bezakan dia di antara bracketing, walaupun 2 titik tapi 2 titik itu tidak bracketkan root tersebut. So it require 2 initial estimate x0 and x1. However, because fx is not required to change the sign between estimate, then it is not classified as bracketing method. So we classify this as open method. The second method, scan, not scan. The second method has the same properties as Newton method, and because the same properties as method, so the convergence is not guaranteed for all chosen value of x, not x1 and the function fx. It may cause divergence sometimes. So let's see example, the same example that we have used before, which is fx equal to exponent negative x minus x. So right now we want to solve by using second method. Okay. So what we need to do, okay, let's say we have an estimation where our x sub I minus 1 equal to 0 and x0 equal to 1. And let's say we have the solution, the true root exists at 0.56714329. So let us do the first iteration. So for the first iteration, so our x sub I minus 1 is 0 and x not equal to 1. So we can calculate what is the f of each function. So if we calculate by using this formula, so replace x equal to 0, so we get 1. We replace x with 1, so we get negative 0.63212. And remember, we need to create a second method punya formula. So based on the general formula, okay, so we can find the next value of x for the first iteration. So for the first iteration, x1 is equal to 1. So xi xi is 1. So 1 minus f of x is negative 0.62 times the difference between these two, 0 minus 1, and we will get our next point is at 0.6127. And if we calculate the 2% relative error based on the given true root, we will get 8% for the first iteration. Now we continue with the second iteration. So we continue with the second iteration. Now our x0 is equal to 1 and our x1 is equal to 0.61270. So this is the value that we'll get from the first iteration. So we find the f of x for each x0 and x1, and then we use this to find the value of x2. Okay, when we calculate, so we get x2 is equal to 0.56384. And then
we can calculate what is the value of 2% relative error. So if we continue with this third iteration, okay, the third iteration, okay, so our x0 will be 0.61270 and our x1 will be 0.5683 from the previous. So x1 will take the value of x2 and x0 will take the value of x1. So we solve it, then we will get this is the value of our x3. So if we summarize what we have calculated so far until the third iteration, so we will get this kind of table. So we number as the number of iteration. So what is the value of x sub I minus 1? What is the value of xi? And what is the value? Ini yang kita kira. Ini yang kita cari. Ataupun ini yang kita nak tengok. Okay. Ini yang kita ada masa mula-mula. Okay, our initial point kita ada this one. Ini kita kira gunakan this is our we calculate these two from the given function of f. Ini initial value. Dan ini yang kita kira. Yang ini kita kira daripada second method punya formula. So in every iteration, bila kita buat second iteration, so nilai xi sub I ni akan ambil nilai sebelumnya. Dan nilai ni datang mana? So daripada sini. Nilai xi yang dapat di sini akan gantikan nilai xi. So dia akan berulang. So this value of xi akan jadi nilai xi tolak 1, and then this value akan jadi nilai and new value of xi. So when we use, in this example, when we use second method, we can see that when we reach the third iteration, the approximate error, the relative approximate error ni have been greatly reduced to 0.0048%. So kita boleh stop kat sini. So bila kita sampai third iteration kita stop. Then root kita nak kat mana? Root kita tengok dekat nilai x sub I plus 1 ni. So this is our assumed root value is 0.5672. So bila kita stop je, kita akan tengok nilai x sub I plus 1 is our referred root value. So kalau kita compare second method, so if we compare between the second method, Newton Raphson method and fixed point iteration, okay, yang mana yang lagi cepat proses dia? So, tadi fixed point untuk example yang sama kita perlukan 10. Untuk Newton Raphson kita perlukan tadi berapa? 4 kan? Untuk second method kita perlukan sekarang berapa? 3. So dari sini kalau kita buat ranking, yang pertama yang paling cepat adalah second method, 2 adalah Newton Raphson, 3 adalah fixed point lah. Setakat ni lah, setakat method kita belajar ni, kita nak buat ranking. So kita buat second method yang pertama, Newton Raphson yang kedua, fixed point yang ketiga. Tapi tengok juga lah, bergantung kepada function apa yang kita gunakan lah. Kadang-kadang kamu akan dapat Newton Raphson lagi cepat untuk diselesaikan berbanding dengan menggunakan second method lah. Ada ketikanya lah. Cuma kelebihan second method adalah kamu tak perlu cari derivatif dia. Kamu tak perlu cari ni f prime x. Tapi pengiraan dia tu kalau dia buat table tu lagi banyak komponen kamu kena kira lah. Kamu kena kira s xi minus 1, f untuk dia, untuk x ni pula f dia, baru kita boleh kirakan apa nilai xi plus 1 berbanding dengan Newton Raphson lah. Second method lagi banyak benda yang kamu kena kira sikit, tapi interaction number dia lagi sikit lah berbanding dengan Newton Raphson. Okay, ada persoalan sama kita tamatkan kita punya sesi untuk hari ini? Soalan?